Hi guys, welcome back to Geometry. It's Mrs. Brunk again. And I think we've probably spent enough time talking about parallel lines in this unit that we've been studying. And I think it's time to talk about another special pair of lines, and that's perpendicular lines. So perpendicular, that's a really common term, and you probably already have in your mind an idea of what that means. And you've talked about perpendicular lines in prior math courses, but even just in terms of everyday life. When you think of perpendicular, you probably think of right angles, and you would be correct. So our learning goal today is to be able to define what perpendicular lines are and to use the perpendicular bisector theorem properties to find side lengths and angle measures. So recall, perpendicular lines are lines that cross at 90 degrees. So just as we mentioned, when you kind of conjure up that idea of perpendicular lines, you think 90 degrees, and that's exactly what is true about perpendicular lines. And sometimes they'll actually label the angle that perpendicular lines make as 90 degrees, and sometimes they'll just simply put a little box in the corner, and that really means the same thing as saying 90-degree angle. So using symbols, so we learned that this, like the two vertical lines, or maybe sometimes they're a little bit slanted, that means parallel. And the upside down T is how we say a symbolic way to say two lines are perpendicular. So we actually draw a pair of little perpendicular segments to use as a symbol. So how we would read that would be like, for instance, here we'd say L is perpendicular to M, or we'd say line XY is perpendicular to segment AB. And then the first theorem that relates to perpendicular lines is the perpendicular bisector theorem. And what that says is this, is if a point is on the perpendicular bisector, so perpendicular and bisector, well, think about what those two things mean. Perpendicular means at 90 degrees. Bisect means to cut into two equal parts, right? We know bisector from other things we studied in geometry. So if a point is on the perpendicular bisector of a segment, then it is equidistant, which means same distance from the end points of the segment. Okay? So for instance, in this drawing over here, we are told that XY is perpendicular to AB. And if we happen to know that if, for instance, that we knew that the segments on either side were equal, then what we could say is if we picked a point on the perpendicular bisector, so say this point X, then we would know that that distance to the endpoints of the segment would have to be the same length. So those distances from the points on the line, any point on the line, so like those would be equal. Or let's say we put a point right here. That point would be the same distance from the endpoints, so these would be equal. Or if you put a point down here, okay, like say this point right here, then these segments would be equal. So any distance, or any distance from a single point on a perpendicular bisector to the endpoints of the segment it bisects would always be the same length. So the first thing we're going to do is take a look at applying the perpendicular bisector theorem. So it says, use the perpendicular bisector theorem to answer the questions. And we're going to use this diagram. And in the diagram, BD is the perpendicular bisector of AC. So what that means is, and they've already marked this for it, but we know it's perpendicular to AC. We also know it bisects AC, so that's why these are marked equal. Okay. And they went on to say, well, suppose the distance from E to D, so right here, this length right here, is 16. And suppose from D to A, so that's, I'm going to highlight that in a color. Let's go yellow right here. And that is 20 centimeters. They want us to find DC. Well, first of all, DC right here would have to be the same as AD, right? Because, again, that's the perpendicular bisector of the segment, so those would have to be equal, so it would also have to be DC would have to be 20 centimeters. Okay. So now they're going to give us some new information. So I'm going to erase this. Same given, though, that BD is the perpendicular bisector, so we still know that that is true of AC. And then they go on to tell us that EC, so from E to C, let's see. So, see if I can get in here and label that. From here to here is 15 centimeters. And then they said from B to A, so B to A, right here, oops, B to A is 25 centimeters. And they want us to find BC. So BC, first of all, one of the things that they gave us that we really didn't need is we didn't really need to know what EC is. We did know already that EC and AE are equal, that's already given, but giving us the actual length being 15 was irrelevant to finding BC because BA was 25 and BC would also have to be then 25 because, again, B is on the perpendicular bisector, so it's got to be equidistant to the M point. So that means these segments right here have to be equal. So it'll be 25 centimeters. Go ahead and try another one together, and then we'll have you try one on your own. So in B, it's given that WY, this line right here, is the perpendicular bisector of segment AB. So right away, I'm going to go over here and I'm going to do some marking on my drawing. So I know if that's the perpendicular bisector. We've already got the 90-degree angle marked, but it means that these two, there you go. We know those two little segments are equal in length. And we also know that any point on the perpendicular bisector, so like W or Y, are going to be equidistant to the M points of segment AB. And so that means like these two segments are equal, to each other as well. And if there were, say, segments here connecting to Y, like this, I'm sorry, my stylus is not working today. So if there were segments drawn there, those would be equal as well. They want us to find some lengths. Let's see if we have enough information to find all of them. So the first thing they ask us to find is WA. So they want WA, this part, this part right here. Well, we can already tell that that has to be 27. Because if we look over on the other side, it's marked 27 on the other side. So 27. XA. So now they want us to find, from X to A. And we can see from X to B, it's 18. So that would have to be 18. And then they want to know what AB is. Well, AB is this entire length right here, right? And we have two parts that are both 18, and 18 plus 18, or 18 times 2, is 36. So now it's time for you to give this a try on your own. So we're going to go to C. This will be a you try question. So take a moment and look at the given information, look at the things that are labeled on the drawing, and any additional things that you can tell by knowing that CE is the perpendicular bisector, and find the 3 missing lengths. So pause the video now, and once you've given that an attempt, tune back in and let's see how you did. Pause now. Alright, so thanks for giving that one a try. FG, which would be this full length right here. Well, there was one part that was 9 and the other part is equal to it, so 9 times 2 is 18. The part FD, which was included in that finding that segment, was 9. And then CD right here, CG, was the same as this one over here, so that one was also 8. Now remember in the last lesson we talked about converses, and we said, well, sometimes theorems have converses that are true. Well, let's think about the perpendicular bisector theorem. So it said, if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of a segment. So the converse of that statement might say something like this. If a point is equidistant from the endpoints of a segment, if a point is on a segment and is equidistant from the endpoints of the segment, then it is on the perpendicular bisector. So something like that. A little wording might be a little different. Think about, would that be true? And in fact, it actually is. So there is a converse theorem because it is true that if a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector of a segment. So you can use that theorem in the reverse. So if a point is equidistant from the endpoints of a segment, then it must lie on the perpendicular bisector theorem, or perpendicular bisector. Now that might even make you think, what about if the point is actually on the segment? Well, if let's say we had a segment, oops, not a line, but a segment, right? And we had a point that is equidistant from the endpoints. We could have a point right here, and if it was equidistant, okay, it still would be on the perpendicular bisector, because if we put a line through that point, which is the midpoint, right, that would be the perpendicular bisector. So even the point actually on the line, or any other point on that line, like say this one right here, this one right here, this one right here, and so on, all those points are going to be equidistant from the endpoints. So this time the converse of the theorem is true. Now, earlier on in the course we talked about like one of the most famous theorems in geometry. It's called the Pythagorean theorem. And we're just going to recap that again. So remember, the Pythagorean theorem is used when you have a right triangle, and it states that for a right triangle with legs called A and B and a hypotenuse called C, so in other words, if the legs are A and B, and remember the legs form a 90-degree angle, they form the right angle, in other words, they're perpendicular, then what's always true in a right triangle is that the sum of the squares of the legs is equal to the square of the hypotenuse, or the famous statement A squared plus B squared equals C squared, or leg squared plus leg squared equals hypotenuse squared. Well, we can use that converse of the perpendicular bisector theorem and the Pythagorean theorem together to solve some problems. And let's take a look at some of those problems that we can solve using this. So this time we're given a drawing that looks like it could be like a triangle with a segment down the middle, cutting it in two pieces. But we're told that AD is 10 inches long. So on this drawing, from A to D is 10. We're told that from B to D is 6, so B to D is right there. And they want us to find AC. So they want us to find this whole length right here. And we know that if these two things are marked equal, these two segments are marked equal, the segment AD and DC, we know that this segment BD must be on the perpendicular bisector. Like if you were to extend this out, that would have to be the perpendicular bisector. And what that means then is that these two segments down here have to be equal. And because then that's also the perpendicular bisector, that has to be a right angle right there. And so what we've created is two right triangles. And one of those right triangles, if I redrew it, looks like this. It's got a leg that's 6, it's got the hypotenuse that's 10, and it's got this unknown that we don't know that we could, let's say, call that A. So we could use the Pythagorean theorem and say something like this: A squared plus 6 squared equals 10 squared. And A squared then plus 36 must equal 100. We could subtract 36 from both sides, and that would leave us with A squared equals 64. And how do you undo a squared? Well, you square root it. So if we just want to find A, we square root. And that's going to give us 8, or negative 8. But because we're talking about lengths of sides, it's going to have to be 8. So we know that this length we called A was 8. So in the drawing, that means this part right here is 8. And that means the part on the other side is 8. And what they ask us to find AC, we now know must be 8 times 2, or 16. Okay, so how about part B? In part B, we have a new drawing, and this time we're told that PA is equal to PC. So I'm going to mark those the same. So PA and PC over here are the same. And then AB, so from here to here, and BC over on this side are also equal to each other. So right away, again, we can kind of make this conclusion using that converse theorem, is we could say, well, this line right here has to be the perpendicular bisector then, because you can see on either side we've got these lengths that are equal. Like We have over here that PA and PC are equal. Okay. We also have over here that AB and BC are equal, and that satisfies the converse theorem, that converse of perpendicular bisector theorem. And so we can conclude that that's perpendicular, which means we can also conclude that this is, that not only is that the bisector, but it's also perpendicular, which means we've got this right angle right here, so we've divided this up into two right triangles again. And it says suppose that PA is 13. So they're telling us this part's 13 and that PB is 5. So again, if I pull this out, and oh, by the way, these, the 3 and the 4 are actually labeling angles. That's not a length, that doesn't say that the length of AB is 3. That's just identifying we have angles 3 and 4 and we have angles 1 and 2. And those are the referring to the angles. But they want us to find the length AC. So we could use that whole idea of the right special like triangle right here, the right triangle. And this time we have, we know that we've got this part being 5. We've got the hypotenuse being 13. So I'm just kind of cutting off and taking one of those little right triangles. And then we can use Pythagorean's theorem again and say, let's say we call this A squared plus, 5 squared equals 13 squared. So again, it's the sum of the squares of the legs is equal to the square of the hypotenuse. So A squared plus 25 equals 169. If I were to subtract 25 from both sides, I'd end up with A squared equals 144. And then to undo the squaring, I'm going to square root just to find out what A is, and the square root of 144 is positive 12. So that means from A to B, that's 12, but they wanted to know the whole length from A to C, which would be 12 times 2, or 24 units long. So there's a couple examples of finding lengths using the converse of the perpendicular bisector theorem and the Pythagorean's theorem. And we're going to wrap up this lesson by finding some angle measures in diagrams using the idea of a perpendicular bisector. So now our focus is going to be looking at angles instead. So example 3, find the measure of the angles in the diagram below. And you see all these labeled angles, X, Y, Z, W, V. Want to know all those. Okay? So what is the value of Z? Well, first of all, Z is this whole angle right here, right? And we know for many reasons that that in fact that's a 90-degree angle. Number one, because they said A and C, so line A and line C were perpendicular, right? So we know that that makes 90-degree angles. But the other thing is we've got this vertical angle concept that we talked about, and we have this angle on the other side over here that's also marked as a 90-degree angle. So this one has to be 90. So that's 90 degrees. And then they go on to say, well, what if Y is 50 degrees? So I'm going to label Y as 50 degrees. And they want us to find the value of X. Well, first of all, if Y is 50, and we know that these are all right angles, like this is a right angle, this down here, that one was, Z was a right angle, all the way around these are right angles, right? So that means that angle X has to be the rest of the 90 degrees. So 90 minus 50 is 40 degrees. So X would have to be 40 degrees. And then what about if V was 60? Now, first of all, we know that V could never be 60. And the reason why is because it has to be the same as Y. But we're just kind of assuming they're giving us new information for a different part of the question. But because we know that this angle right here and angle Y would have to be vertical angles, they'd have to be the same. But, so new problem. So if V is 60, what is W? Then W would have to be the rest of 90. So again, that would be 30 degrees because 30 and 60 is 90. And the final one. And the drawing's starting to get more and more complicated all the time now. Now we've got some lines that look to be parallel. And it looks like we are given some information that they actually are parallel. So B and D are parallel, so I'm going to mark those with those little arrows to show those are parallel. And C and E, so we know that these lines, and by the way, when you have multiple pairs of lines parallel in a drawing, but not all parallel to each other, you can use single arrow on one, double arrows on the other, but just to, so you distinguish which ones are parallel to each other, even though it's very obvious here. And then they go on to say that the measure of angle 1 is 50 degrees, and the measure of angle 5 is 90 degrees. So as we work our way through here, if this angle 5 is 90 degrees, then angle right here that's made up of 2 and 6 would also have to be 90 degrees, right? So, because actually all those angles down here all have to be 90. Okay, if one of those angles that's formed by those two lines is 90, they're all 90. So there's a couple ways we could go about finding this angle. I guess they didn't actually even ask us to find. Wants us to maybe find all the other ones that are listed, I guess. So they want us to find angle 2, although it doesn't really say that. But they want us to find the measure of angle 2, because we don't know that one. I guess they want us to find the measure of angle 4, the measure of angle 3. We already know the measure of angle 5, and we know the measure of angle 1. So it looks like we just have to find, and the measure of angle 4. I didn't see that. Oh, I wrote 4. 4, 3, 2, I guess we need to know 6. So all the ones that are missing there we're going to find. So let's start digging in and see what we can find. So first of all, if the measure of angle 1 is 50 degrees, and if you look at just these parallel lines, okay, oops, I'm going to highlight them in yellow, just this one and this one. And if you look at this angle that we know to be 50 degrees right here at 1 and 2 would have to actually be corresponding angles, right? Because there's a transversal right there, and they're in the corresponding position, and that means angle 2 must be 50 degrees. Okay, so if angle 2 is 50 degrees, then angle 3 must be 50 degrees because those are vertical angles, right? So they're opening in opposite positions. So we've got 2 is 50. We've got 3 is 50. Okay, if angle 3 is 50, angle 4 must be 40 degrees because the two angles together have to make 90, right? And then if angle 4 is 40, then angle 6 must be 40 also because those are vertical angles as well. So just knowing this relationship between parallel lines and now the fact that we have one line that's perpendicular to one of those parallel lines must be perpendicular to the other, and we're able to find all these missing angles. So that does it for the perpendicular bisector theorem and perpendicular lines. Thanks for coming to class.